So we did the design and development of the powered wheelchair attachment sponsored by Lifescape out of Sioux Falls. I am Drew Vandenhall.
I'm Brian Tweez.
Great buzz.
And who is Lifescape? So Lifescape is an independent nonprofit organization serving adults and children specializing in behavioral, physical, occupational, and speech therapy, also as well as psychology. Currently, our design is assisting them in their RISE program. The RISE program provides orthodontics, prosthetics, wheelchair, and mobility solutions to both children and adults. These are our goals and constraints. Overall, the goal is to design a cost-effective attachment, providing mobility to manual wheelchairs. We have state-of-the-art competitors that we'll explain later, and they are that higher price mark. Our ages are from about that 10 to 70. Can be temporary or permanent usage of that wheelchair, as well as the design needs to be easily attached and detached to allow no extra weight on the manual wheelchair, which being nice. 2-range minimum was given to us with a minimum maximum speed, or not maximum speed, a minimum speed of 2 miles per hour. System needs to be purchased for about $500 mark, just to provide for those who are financially more strained and simple, robust, and importance of our project. 1.5 million Americans use manual wheelchairs in the United States, and that takes up about that 90% of all wheelchair users. Over half are 65 years or older. There are very few are eligible financial assistance to purchase automatic wheelchairs and wheelchair attachments due to requiring massive motor disabilities. Studies show 37% of Americans need to borrow money for an unexpected $400 expense. It's exacerbated when you're on a fixed income and are currently in medical emergency or catastrophic.
So here are a few of our competitors that we talked about. So as you can see, there's a few different types. So Firefly and Easy Ride, we call that a front end design, where basically it's a frontal attachment that just clips on, and then they got normal e-bike handlebars, throttle brake. Those are typically cheaper. As you can see, there's also rear-driven drives, like a smart drive is around your $6,000, $7,000 range, whereas your front tug is around $3,000 to $1,000. The smart drive has had a lot of problems with consumers because it's powered by a smartwatch that goes on your hand, and they say that when you're doing the action of pushing it, the smart band is supposed to send that to the motors, but it often doesn't. And that's also countered by the Yamaha Hub, which is another design where basically they swap out the manual wheelchair wheels with an electric powered wheel, which it does work, but yet again, it's very expensive. So here were a few designs that we decided to come up with. We decided the front tug design is cheap, it's reliable, it's simple, robust, lines up good with our goals and constraints. We tried to think about a compression drive, which is a little bit different than what we've seen from other consumers or other customers or other manufacturers, where basically it has 2 little rubber wheels that would compress on the manual wheelchair wheel itself, and then thus drive the motor or drive the wheel. But we decided not to go with that for different reasons. It wasn't as simple, wasn't as robust. Seemed like it could have had a lot of problems down the road. And a third consideration was the hub wheel, which we did like, but after further review with Lifescape, we decided not to go down that road either because of attachability, detachability. It wouldn't be as easy for manual wheelchair. So we decided to go with a front tug design. This is what it looks like. That was the rough sketch on CAD for parts that we were actually able to source online. So as you can see, it's just a general framework. You got your hub wheel down there that connects to the fork, which connects on the inside to a compression quill, which then goes up to your stem, which is foldable and raisable for people of different height and to be able to collapse easily into your car or other places like that. that goes to your handlebars, which again have your throttle on each side. And then on the outside of the fork, it connects to what's called a headset, which allows the pivot motion. And then that is clamped on to 1.5 steel tubing, which allows it to connect rigidly to the frame with the addition of clamps on top of it. As you can see too, we got our sketch here on the battery ESC handlebar throttle. If you want to talk about that, Bryce.
Yep, so this kind of all comes into a package, right? The only addition that we have ourselves is a power switch. Just kind of disconnect that open circuit to allow them to be able to properly remove the battery and not have to worry about discharging and using whatever. So the handlebar directly talks to the ESC. The ESC then that throttle is a potentiometer that directly talks to the ESC. Sends those voltages and currents from the battery straight to the output.
Okay. So for our drive system, at the beginning, our sponsor actually wanted us to basically chop up electric scooter. So instead of actually buying an electric scooter and wasting all the parts from the pieces, we decided to look for a motor that actually came from a scooter or a scooter kit. So we went to Amazon and found a pretty cheap one, ranges from $120 to $160, which is very, very good. And after testing it, it works out very well. We looked for a 24-volt one because the operating characteristics are much better at lower RPMs, which you don't want it to be. You don't want them to go too fast in the wheelchair. It needs to be safe, so we did that. And then it's a really simple installation, so you just bolt it straight onto the works that we have. It all works out perfectly. It's really simple, really cheap too. Very important that this is super cheap because our budget is $500. That kind of slapped us in the face at the beginning of the first semester. We didn't realize it was going to be so difficult to actually source all these parts that we need for it to be within this budget. Because if we ever broke the budget range, like we said, that would basically make this project null for nothing. So we had to make sure it was $500. And this kit was great because it just came with the drag motor, which had a built-in brake, throttle, all in one price. And then onto that brake system, it's really simple, really robust. It's just a drum brake setup, and it's all integrated straight into the wheel itself. And all you had to do was source the actual brake lever, which pulls straight onto the handlebars, and then a simple brake cable.
So on the electrical housing, the target was to design a clean and organized system to house all of our components, as well as be a little bit personalized. So this is 3D printed. You can kind of change the colors just to kind of give that pop, or it's some more variety if you look for it. So there's a couple iterations. As you'll see right here, we still have the 2 battery going in the box that you can see in our bridge test. If you feel like it's necessary, so drop that down to that 1 battery capacity. We also have the ESC connection cover right there. We switched from the heat inserts to then just flange bolts to not require soldering, stuff like that. Also was focused on the watertight or splash resistance and rain resistance, and then also minimum profile and easy installation.
So 3D printing materials, like we said, we did a lot of parts with 3D printing. A big portion of that was just to cut costs to Lifescape as part of our $500 budget. So we started off printing off with ASA. We thought it would be good because it's huge and can handle the outdoors, but we found out that it's very poor layer adhesion and it's very hard to print and it's very expensive. It was about $30 for 1 kilogram, whereas stuff like PLA, PETG, PBTGM, you can all get for about $10 per kilogram. Along with that, with the poor layer adhesion, parts would break easily, and we didn't want that for obvious reasons. So we decided to iterate with PLA for a little bit before getting PETG. PLA, it works good, but there's no UV, so it's not good for the actual consumer themselves to think about it long term. So we went with PETG, which is pretty good UV resistance. It has good strength as well. It's cheap, it's affordable, it's water resistant, which is good for the electrical housing. But we wanted to try PVT GF, which is a new experimental fiber that's on the market right now. It's strong, it's UV resistant, it's flexible, which is good for the clamps. It has good printability, which is nice for Lifescape, but it's really hard to acquire because, like we said, it's still that experimental filament. I ordered some in September, and I was just able to get some now as of last week, Wednesday, I want to say. So it took about 3 months to get it, and even so, that was like the last 2 rolls of filament I was able to get. So we'll see how that works like that. But for structural analysis of the clamps, we tried doing simulations at first in SolidWorks, but it was very unreliable because of that 3D printing aspect. That thing with SolidWorks simulations is that it doesn't actually account for stuff like, geometry, infill, infill percentage or, wall count or type. Basically we had to iterate different designs and then see experimentally, is it better or worse? And then we were able to find a few trends like wall count, 4 to 6 walls was a good number for structural stability as well as printability. If you have too many walls, that tends to bend your print more. Type, we were able to test gyroid, grid, and cubic, and we found that gyroid, it's good structurally strong, but it has real bad layer adhesion, which grid is good at. Grid has good layer adhesion, but it's bad the other way with tensile compression strength. So we decided on cubic, which is a good blend of both structural stability and good layer adhesion. And for infill percentage, we decided between 40 to 90%, 40 for stuff like electrical housing, which isn't under direct load, 90 for absolute dollar under direct load all the time. The big thing about 90 is that it can work with lower infill percentage, but then you struggle a lot more with fatigue strip, which is why you have that higher infill percentage. And so here's some of our clamp design iterations. As you can see here, we started from the left, went over to the right, and now we have a few different models that we haven't included in this too. You can see we had thicker clamps, thicker tabs, which we had to reduce more lever action. And then you can see too, basically we went from round to square to allow it to print better, to adhere better. And with better printability, it lasts better, stronger, stuff like that. But as you can see here, it's $10, $50 for a normal clamp like this, whereas this we can print it out for about $2. So we're getting a good savings with that.
Just going to touch on some of our design process. The start of the semester, we initially got the hub motor. We were kind of concerned some torque was going to be able to provide, and it was going to be able to take that weight and put it up over a ramp. We did test over 120, 180, and 280. We did realize that the hub motor does work in that version 0.1. It does work with all weight classes. There was some issues on higher incline ramps, like the 88 compliant ramps. Then we moved on to version 1.0. That was testing comfort, feelability, mobility, and just kind of how it operates, taking on. We realized it was pretty good after we sat there. Then we got version 1.1, which is an iteration of the brake cable, some of the electrical housing, and just kind of getting the finer details in. And then we finally moved on to our current version, which is the 1.2. The right picture shows you what the wheelchair will have when they're not using it. So we're adding maybe 200 grams of total weight to the wheelchair, which is non-existent for someone doing it. So if they don't want to use it, it's not impacting them too much. And on the left is the final version of our design, including the waterproofing of the charge cable and yes. This is just some of the raw data. So the 280 pounds, we got about the 6.5 miles. The 180 pounds, which is your average weight class for an adult male, and that we got about 9.5 miles. And also on the 120, we got about 10.25. And this was all just that one 10 amp hour battery. So then we obviously axed out that other battery to decrease some of our costs for our. Just a regression model, just something for them to be able to kind of understand where their problem would sit.
So here's some videos. It seems like the one on the right's not working, but yeah, basically you can see thing flies, right? It's going very well. You know, it handles bumps good. Yeah. And here is automatic versus manual. Seems like videos are also not playing for these. But yeah, basically the one on the automatic, it's going 6.8 miles an hour. The manual version's going only about 3 miles an hour, and that's still not the fullest extent of both. But yeah, the automatic, it goes about roughly 12, 15 miles an hour at its full capacity. That being said, you could probably go about 4 or 5 miles an hour manually too, but that's really huffing it, right? It's a lot easier when you just got a throttle in your hand. You're just coasting the way down.
There was a lot of work putting into that three, almost 4 miles per hour. I was sitting there trying to put as much power as possible, popping wheelies half the times. But
yeah, as you can see here, you got a little bit of rougher terrain right there too, and with those little tiny casters on your manual wheelchair, it likes to just wobble like crazy. It's a lot more structurally stable as well, but the automatic version. Here was our off-road videos. See if we can get a couple of Yeah, so here's some of our off-road videos that we did. As you can see, it works well on gravel. That second to the right video there, you can see he stopped and he's able to start up pretty good, just fine. The one in the middle right there, you can see that basically on grass, it's a little harder to get going, but once you get going, you're able to keep it going for a while. Yeah.
and some of our design considerations comparisons. Obviously, cost was the highest of the highest performance. We also came in with installation. Really, Lifescape has limited tools to be able to manufacture these processes. That's why we heavily went on the 3D printing as well, for not buying pre-made plants and stuff like that. Also installation, we don't want, you're not going to want to spend 20 minutes assembling with a full head of tools just to assemble your automatic conversion kit every time you want to use it. So those were our biggest considerations, and under this application, at least with our design matrix, we do show that we do perform better, and mainly that comes with our cost and manufacturability qualities. Then bottom of budget. So again, our target budget was $500. Currently, we're staying at $465, and this actually did lower as of the last couple of weeks because our kit went down about $25. But the assembly is relatively involved. The initial assembly that likes to want to do to customer that's required for the cost that we're going to say at. And then obviously we saved a lot of money going through.
So going back to our goals and constraints, you know, in conclusion, we designed a cost-effective attachment to provide mobility manual wheelchair users that's, you know, around 10 years old to 70 years old, right? And it's good for permanent or temporary manual wheelchair users because, you know, it's cheap and affordable. Like you said, target range under $500. We did that. 2 miles of range, minimum speed of 2 miles an hour. We get about 8 to 10 miles of range and about 15 to 12 top speed miles per hour. Easily detached. We were able to do that with quick connect clamps to easily pop on and take off the attachment. And it was simple and robust. Like we said, that front tug design, it's a lot easier to make a simple design like that. Looking at our competitors, you know, we blow the prices of our competitors out of the water while still keeping the maturity of stats the same. Then 9 miles range, 15 mile range, 12 miles range, 15, 12. We get about 3/4 of what our competitor has, which is about all you need. And all you would need to get more range is just extra battery to add on top of that. Top speed, 15 miles an hour. We're about the same, if not better than all our competitors. Right? You can see the Yamaha Hub and Smart Drive, they only got about 5 miles an hour top speed. And product weight, we're a little bit more than the Yamaha Hub or the Smart Drive, but we're about equal, if not a little less than the other front tug competitors. It's about where we want.
And the nice thing about our design specifically, just real quick, Firefly, right, don't have detachable, easy detachable batteries. We do, you will incorporate that, so they'll be able to actually double, triple, quadruple, depending on how many batteries they would be able to purchase.
Any questions?
I got one. Where did you guys think about human factors? So somebody who needs a wheelchair has to be able to get into it. And that looked kind of complicated to get into it. In fact, maybe not even possible.
I got you. Yep. So, what we have is a lever clamp assembly. So on those two pieces that you saw kind of on, kind of new wheels, we basically have a 3D printed lever clamp and it'll allow, some friction fit. You'll be able to push that in. The handlebar is collapsible and and the handlebar itself with the headset also is on lever clamp assembly. So that'll be able to stay out of your way while you're assembling.
Did you do a human factor study?
We have not yet. We are hoping to do that next.
465 was just parts, right?
Yeah.
And you said installation was complicated.
Lifescape is going to be providing there is going to be no labor cost from Lifescape. They're providing these to their customers and assembling them for them. So they'll be only worried about the material cost.
So realistically though, it's about $1,500, not 465.
If you were to add labor, possibly, yeah.
Like on that 24-volt motor that you used from a scooter to make this drive, if like that motor went out for some reason and like that exact motor wasn't available, is that a component that could be easily swapped out with like a similar motor, kind of like on Amazon or something like that? Or
As long as it's a 24-volt motor, you know.
Oh.
There's actually quite a bit. Just the individual.
These are all e-scooter kits, so anything, they're pretty, I apologize. They're pretty, standard, when they come with their ESCs. We try to get a couple of models, so they all work. Some of them do have a little bit more, oil learning, but they all work.
We'll definitely that problem a little bit in the spring, with a lot of China parts coming out. It seemed like, we struggled, our parts would go down for some time, but then we were able to find, the same ones from a different company, different supplier, within like a day of researching, able to find like 4 or 5 different lengths of supplies.
Did you consider safety factor in your design? If yes, what is your safety factor?
Absolutely. So when we initially finding our wattage for our hub motor, we were going for at least a 1.8, just kind of give at least that, any losses through friction. Obviously weight's not all entirely on that wheel, so you're has to slippage or stuff like that. So we wanted to make sure that's in a, though we did come into issues because we're looking for very cheap ones. We don't have those torque data for a lot of these motors. So we had to basically assume and hope when it came to wattage that was game. And that's why we did a lot of that testing with initial semester to make sure we do have that.
So you mentioned the switch for the system. Does that function as an e-stop too? So you just flip it off to turn off the motor?
Yeah, they completely opens the circuit.
do you need any tools to swap out the battery, or is it some sort of quick disconnect system?
Just a quick disconnect system. So there's just some of the things that they use for last club, just some of those I don't know called they're just battery. So
XT60, is that just the phone connector?
Yeah. So it's easy.
How does your BOM and budget scale? If you were mass producing 10, 20, 30, how does that handle that?
That we don't know. ourselves. That might be something Alibaba and AliExpress do, offer some budget and could improve some of our, material costs, but we haven't done that yet.
As for scalability too, it'd actually be very nice for a lot of our parts, because then we wouldn't have to pre frame anymore, you might just be able to get
Yeah.
injection mold, you get a much better product.
Let me ask this one. If I'm a potential user, I'm impressed by your wheelchair and I want to buy one from you, how much are you gonna sell it to me?
It'd be $465, it's the cost of our materials.
But you should also add your time, manufacturing cost and profit.
Lightscape, doesn't want to do any of that, so their
Okay.
customers come up with physical, the physical mobility issues, PT, stuff like that. When they're in those times, all they want is them to buy materials, Lightscape will assemble and then provide that for them. It's not gonna be it's not necessarily a multiple item that's gonna be product or something.
Yeah, it's, we didn't cover that enough, but they're actually nonprofits.
Nonprofit.
Not looking to the point where they're looking to buy better.
So what batteries do you guys use? Is it like LiPo? Is it like stuff that's like
It is 24 volt and